frame which is accelerating, we must take into account the acceleration of the frame by accounting for a force called the pseudo force, which makes this frame inertial. Without doing this, we cannot apply the laws of motion accurately. Friction is the next thing which is really important. Understanding friction and its applications in various problems is often tricky. Use this golden rule. Friction always opposes the relative motion of surfaces. The aim of friction is to try and keep two bodies moving together. Therefore, if there is one block on top of another block and the lower block is moving, friction tries to push the other block in the same direction. Friction opposes relative motion. The value of the friction force is equal to the applied force as long as the body is at rest. Therefore, it requires a certain minimum force to try and move a body that is kept upon a frictional surface. This maximum value is mu s into n, where mu s is the coefficient of static friction. N is the normal force that is applied on that surface. The value of mu s depends on the type of surfaces. There are many kinds of surfaces, some which generate more friction than others. There is no restriction on the value of mu s, it may be more than 1. In all of these questions, be sure to draw a proper, clear and accurate free body diagram. All the equations that you will write will be derived from this free body diagram, and any mistake that you make in drawing the FBD will be carried on to your equations. So be clear about what the problem is saying and draw an accurate FBD. What are some of the common doubts that people have? They're on applying the pseudo force concept. The pseudo force concept is somewhat tricky. In an accelerating frame, in order to take into account the acceleration of the frame, we must apply a pseudo force. Once the pseudo force is applied, you can consider the frame to be inertial and solve your problems using the same laws of motion. If that force is ignored in the equations, then the result will of course be wrong. The other doubt is on finding what frictional force is there. Here, always rely on the golden rule. Friction opposes relative motion. As long as the body is at rest, the force that is applied is a maximum of mu s n, and once it moves, then the force depends on the kinetic friction that is there. Let's go on to work, power and energy. The reason these concepts are so powerful is because there are conservation laws associated with them. What does this mean? If you have a situation, lots of things change, and then you have another resultant situation. With only information about the initial state and the final state, you can derive many useful conclusions. What is the conservation law associated with work, power and energy? The conservation of energy, that the total initial energy of any system is equal to the total final energy. What is energy? Energy is the potential to do work. Whenever work is done by any force, it is transferred into the energy of a body. We must always take into account the work done by a force when applying the principle of conservation of energy. Work is defined as the displacement caused due to a force. The formula is integral F ds. Therefore, with every force that acts on a body and causes it to move, we must calculate the associated work. Remember that since forces are frame dependent, work is also frame dependent. The student should be comfortable while applying the work energy theorem. Correctly identify all the forces which are performing work. Make sure that you don't miss anything out. Add the works correctly with due regard to the sign of that work. When the reduced mass concept is applied, make sure that you understand exactly how it is applied in that particular situation. If reduced mass is used to simplify a particular concept, make sure that you take all the forces that were applying on the different masses which have been reduced, and that the work done by all of them is appropriately calculated. Also remember that the energy of any particle which is bounded, that is, it is under some attractive force, is negative. Because if a particle is within a gravitational body, it wants to be close to that body, it requires energy to try and separate the particle from that body. Therefore, its own energy is negative. Rotational motion is a step ahead of what we've been doing so far because it introduces additional complications. We'll be dealing with extended bodies because rotation, after all, is not possible with a point. Our strategy so far has been to reduce any system to point particles, then apply either the laws of force or the work energy principle or the principles of linear momentum and try and solve the system. In rotational motion, we have similar concepts. But along with the previous equations, we'll now be dealing with new laws. The law of torque and moment of inertia, the law of conservation of angular momentum, and the law of work energy taking into account rotational energy. So let's come to this concept of moment of inertia. Just like we had the concept of mass initially, we'll now be using the concept of moment of inertia, which is the rotational effect of a body calculated about certain axes. The choice of these axes are very important in solving a problem. To calculate the moment of inertia of a point body, we use mr square, where r is the perpendicular distance from that axis. To calculate the moment of inertia of the extended body, we thus use integral dmr square. There are two theorems that allow us to make use of information of moment of inertia about particular axes and transfer that information to other axes. They are the principle of parallel axis theorem and perpendicular axis theorem. Keep in mind that the parallel axis theorem can only be used when one of the axes is passing through the center of mass. We then have the total energy of the body. The kinetic energy of the body is of two components. The linear motion energy, which we have already calculated, the translational energy, and now the rotational energy of the body, which must be taken into account both initially and finally. Another complication that comes over here is the direction of frictional force. And this is particularly strange in rotational motion because often you have a body moving in one direction, but its rotation causes the point of contact's velocity to be in the other direction. Thus it appears that friction is actually supporting the translational motion of that body. The error that we make here is that friction tries to oppose relative velocity at the point of contact between two surfaces. Therefore, if a body is rotating in a particular direction and this causes the point of contact's velocity to be in a particular direction, then friction will oppose that direction. Therefore, make sure that you do not make an error in the way that we apply the frictional force. Take the example of a disc rotating on a table. Imagine that the disc is moving towards the right and the rotation of that disc is clockwise and quite fast. In what direction do you think the frictional force should apply? Intuitively, it may seem that the frictional force should apply towards the left, since it should oppose the motion of the body. However, if the rotation of that disc is fast enough in the clockwise direction, then the velocity of the point of contact might well be towards the left. Since friction tries to minimize this relative velocity and bring it to zero, the frictional force would apply to the right, in the direction of translational motion, but opposing the resultant velocity of that point of contact. It's important to avoid this particular common error. We can also use the principle of conservation of angular momentum. This is used in addition to the principle of conservation of linear momentum, but it's important not to make mistakes in its application. Choose a good point or axis for the conservation of angular momentum and take into account the angular momentum of every body or parts of the body which are rotating. Another common concept that is sometimes useful to solve particular problems quickly is the instantaneous center of rotation. When we have an extended body or system, sometimes we can calculate its instantaneous center of rotation and apply the laws of rotation about that particular point. This results in a particularly simple form, enabling us to solve the problem quickly. It's also important to know the conditions for rolling and for toppling. Let's talk about simple harmonic motion. What this essentially means is the to and fro motion of a body. For instance, a pendulum or a ball attached to a spring. There are two approaches to try and solve this problem. We need to discuss the dynamics of that particle which is moving to and fro. Therefore, we need to know its velocity at various points, the forces acting on it, and how these change as the motion progresses. We can either write down directly the force equations. For instance, if you have a ball attached to a spring, the force on it would be minus kx, where k is the spring constant and x is its distance from the mean position. Alternately, what we can do is write down the energy equation. That is, total energy is equal to a constant. This is sometimes easier to do in some harmonic questions. Then we differentiate this particular equation to get the derivative of total energy is equal to 0. This equation is essentially equivalent to the force equation and can be used to determine the dynamics of that particular body. It's simply a matter of what you think is easier to write accurately in that particular question. Of course, all this depends on knowing the equilibrium position. To calculate the equilibrium position, identify the point where forces are zero by either of the two methods specified above. Once you do this, your problem will simplify considerably. The magnitude and direction of the restoring force depends on what is causing the particular motion. For instance, if a pendulum is making small oscillations, then the restoring force may well be gravity. In a spring, the restoring force is that of the spring. Write the equation accurately, correctly, and find the restoring force as a function of the distance from the mean position. Similarly, we must know how to calculate the energy in the mean position and all intermediate positions. So consider a spring and a ball attached at the end. Energy is constantly being exchanged between these two particular bodies. So at the equilibrium position, since the velocity of that particular body will be high, the energy is stored in the form of kinetic energy of the body, and the spring itself has no energy. However, at the end points where the velocity of the body is zero, it has no kinetic energy, which has all been transferred into the potential energy of that spring. In any intermediate position, the energy is divided such that the sum remains constant.